A nuclear reactor can cost more than $10 billion. Take 10 or 15 years to build and still be not ready when the world needs the power. That is the problem. Not that nuclear power does not work, not that we do not understand the science. The problem is that building the physical reactor has become one of the hardest industrial projects on Earth. A country can announce a nuclear plant today. Politicians can promise clean baseload power. Energy companies can sign contracts. Engineers can finish the design. But the reactor itself still has to be built. Concrete has to be poured. Steel has to be certified. Components have to be manufactured. Workers have to be trained, inspections have to pass, and the construction site has to keep moving for more than a decade. This is where the promise breaks, because nuclear is often presented as the answer to the future of energy. AI data centers need power. Factories need power. Cities need power. Electric grids need stable supply. And nuclear looks like the perfect solution. But there is one problem. The world needs electricity now. Nuclear reactors arrive later, sometimes much later. And the reason is not simple, because the real bottleneck is not the reactor. It is the construction clock. Once a nuclear project starts, the clock begins to attack the project from every direction. Every year of delay increases financing costs. Every inspection adds risk. Every design change creates rework. Every missing supplier pushes the schedule. Every political cycle adds pressure. And every month the reactor remains unfinished, the project becomes harder to save. This is why nuclear construction is so different from most technologies. Software can be updated. Factories can sometimes be expanded. Data centers can be built in phases. But a nuclear reactor is a massive physical system. It cannot be scaled by pushing code. It cannot be accelerated by hype. It cannot be fixed with one new feature. It has to be executed year after year, layer after layer, inspection after inspection. And that is what makes it so dangerous. Because the longer construction takes, the more the project stops being an engineering challenge and becomes a financial trap. The reactor is not producing electricity yet, but the money is already being spent. The debt is already growing. The workforce is already mobilized. The suppliers are already locked in. And the public is still waiting. So the real question is not just, why does nuclear take so long? The real question is, who can survive long enough to finish it? And this is where the reactor stops looking like a power plant. It starts looking like a construction monster. A nuclear reactor is not a normal power plant. It is a decade-long construction trap. Before a single watt reaches the grid, the project needs a giant construction site, thousands of workers, nuclear-grade components, massive concrete structures, cooling systems, turbines, certified suppliers, safety inspections, and financing that can survive year after year of delay. This is why the thumbnail says, "Not ready." Because the problem is not that nuclear power is mysterious. The problem is that building the physical system takes brutal amounts of time, money, and coordination. A single nuclear project can move past $10 billion before it is finished. Some projects stretch toward 10 or 15 years of construction, testing, rework, and approval, and every year matters. Because in nuclear construction, time is not just time. Time is cost. Time is risk. Time is political pressure. Time is financing. Time is the construction clock. And once that clock starts running, it becomes the invisible villain of the entire project. Because the project does not fail all at once. It slowly gets heavier. Every delay adds another layer of cost. Every missed milestone makes the next one harder. And every year the reactor remains unfinished, fewer actors can afford to keep going. The real bottleneck is not knowing how nuclear power works. The bottleneck is building the damn thing. A reactor is built from parts that cannot simply be ordered from a normal industrial catalog. Many components need certified suppliers. Certified suppliers are rare. Rare suppliers create long lead times. Long lead times create delays. Delays increase cost. And higher costs pushes weaker players out. That is the first chain. Safety requirements create supplier scarcity. Supplier scarcity creates waiting. Waiting creates overruns. Overruns create exclusion. But there is a second chain inside the construction site itself. A nuclear plant has thousands of interfaces. Concrete, steel, pipes, cables, control systems, cooling systems, containment structures, turbines, sensors, inspections. Everything has to fit. Everything has to be sequenced. And everything has to pass a higher standard than normal construction. So one mistake does not stay small. One weld problem can trigger inspection. One inspection can trigger rework. One rework package can stop the next stage. One stop stage can push the schedule. And once the schedule moves, the money starts to break. This is where nuclear construction becomes different from ordinary infrastructure. In a normal project, a mistake may be expensive. In a nuclear project, a mistake can become a delay multiplier. It can freeze work. It can force redesign. It can reopen inspections. It can turn a local problem into a project-wide cost shock. This is why nuclear construction becomes so dangerous financially. The project is not just expensive because the reactor is advanced. It is expensive because the construction process keeps absorbing time. And the longer it lasts, the harder it becomes to finish. This is not theoretical. Vogtle in the United States, Flamanville in France, and Olkiluoto in Finland all show the same pattern. Rich countries. Advanced engineering, serious industrial capability, and still, years of delays and major cost overruns. The point is not that nuclear is impossible. The point is that nuclear construction punishes any system that cannot sustain execution for more than a decade. And that changes who can play the game. Most companies cannot survive a project where the final cost may be several times larger than the original estimate. Most utilities cannot absorb endless construction risk without state support. Most countries cannot build the supplier base, workforce, regulatory capacity, financing structure, and grid infrastructure at the same time. Because nuclear does not only require money, it requires patient money. It requires political endurance. It requires suppliers that can survive slow demand. It requires workers who can execute specialized tasks for years. And it requires a system willing to keep paying before the reactor produces anything at all, so nuclear power becomes structurally selective. It is not available to everyone who wants clean baseload electricity. It is available to whoever can survive the construction clock. That is the real consequence. High cost creates pressure. Long timelines create risk. Execution risk creates exclusion. And exclusion concentrates power in the hands of the few systems that can keep building while everyone else is forced to wait. Because in nuclear, power belongs to whoever can survive the build. And this is the part that changes the story. Nuclear delay is not just a scheduling problem, it is a power structure. The reactor is only the visible part. The real power is in the system that can finish it. Because if a reactor takes more than a decade to build, then nuclear power is not available to everyone who wants it. It is available to whoever can survive the build. That means whoever has patient capital, whoever has state support, whoever has certified suppliers, whoever has skilled workers, whoever has political endurance, Whoever can absorb years of delay before a single watt reaches the grid. This is why the bottleneck is not nuclear science. Humanity already knows how nuclear power works. The bottleneck is building the damn thing. And once you understand that, nuclear starts to look different. It is not just an energy technology. It is an industrial execution test, a test of capital, a test of supply chains, a test of construction capability, a test of whether modern industrial systems can still build gigantic physical infrastructure fast enough. The countries and companies that pass that test gain something far more valuable than a power plant. They gain control over one of the hardest energy bottlenecks in the modern economy. The future of energy may not be decided only by who has the best technology. It may be decided by who can still build at impossible scale. Because the world can demand more electricity, AI can demand more power, industry can demand more capacity, governments can announce more reactors, but none of that matters if the physical system cannot be built fast enough. That is the real lesson of nuclear construction. The science matters, the regulation matters, the politics matter, but the deepest constraint is execution. Who can finance the project for 10 or 15 years? Who can keep the suppliers alive? Who can keep the workforce moving? Who can survive the delays, the overruns, and the construction clock? In nuclear, power belongs to whoever can survive the build. Money buys access. Access creates dependence. And dependence becomes control. And this is the industry code.